computational methods and simulating equilibrium electronic structures. And so on this next slide, we want to take a look at some of the results. And so here is going to be a video, and this is the initial potential, and this is going to be the initial wave packet. And the way that we've decided to label the reaction coordinates is in total dipole of the molecule. And so when Sheldon was giving his presentation, he was talking about electron movement within the z direction, or on the z-axis, after integrating the x and y directions. And so what I've done with the model is in the direction of the charge transfer and going from the porphyrin to the quinone, we've set it up so that the charge will go along the z-axis. And so what I'm going to do is I'll start the video. And so as we see this initial wave packet, the total dipole values and the way they're determined is based on the total charge of the nuclear and the center of the charge of the electronic. And so when looking at these dipole values in relation to the ground state, we see that the electron is going to be initially excited from the ground state to the second excited state, making this first transition from the second excited state to the first something worth looking into. And so as we see this blue wave packet within the second excited state is moving in time, and you can see that here within the reaction coordinates, but also during this oscillation, as the wave packet moves towards the interaction potentials, you're seeing part of the wave packet being transferred, and you're going to see wave packet population within this bottom graph representing the S1 potential. Now, as this oscillates back and forth, we're seeing a population and a plateau, and all the way up to this peak. But when we come here, we're seeing this oscillation within the lower potential and some of the wave packet being translated back into the S2 potential. And so this was the rate after putting in initial conditions of momentum and after determining some of the non-adiabatic coupling term. So we're looking around 3 picosecond for this transition from the second excited state to the first. And you can see that the red line for the potential, the wave packet in the first potential is changing a little bit and changing vibrational energy states. And so we're assuming that as this center of charge of the electron is transferring, we're also seeing shifting of nuclear motion, and that nuclear motion is also interacting and changing the energy states. And so from my conclusions, we were talking a little bit of how we can use MATLAB as a viable tool, and in this case, moving beyond some of the Born-Oppenheimer approximation. We also found this rate to be very fast and within the time scale that is desired, and the time evolution of electronic population can help give indications of the nuclear motion within the system. So,
okay,
thank you.
Thanks, John. And any questions are very welcome.
I do have questions. So you said that there are non-adiabatic terms that you're dealing with, that you draw your potentials as adiabatic. So
the potentials, yes, are drawn as in a harmonic way, and more or less we know that's not typically the case within real time.
But aside from just harmonic, I mean, usually in the non-adiabatic case, those potentials are connected in some way. Is that that's my understanding of it, how I normally see that discussed. Do you know what I mean? Instead of totally separate, if you have two coming together, they actually have a well between them and a barrier between them. Is that not what that means? Does this mean something else?
I guess I would have to refer
Okay, I'll help.
on that question.
So the parameterization and pictures of potentials that Jon is presenting are in the it's too much complicated diabatic basis.
Okay.
Then there is a next step. One takes into account the presence of some always persisting coupling between them, and one diagonalizes them and come into the adiabatic basis when one has the lower potential with two wells and upper also something complicated.
Right.
And those are eigenstates, and they do not communicate to each other at low kinetic energy. And then the third level, when energy is high enough, one switches on non-adiabatic mechanism to jumping between them. But this would be, the whole story would be too much for educational project. Okay, more questions to the speaker. I think you already told it during the presentation, but can you clarify once again, how did you define initial conditions for your wave packet? What were your initial position of the center of the wave packet, and what was the initial momentum?
So
And draw more things if you need.
then I guess in this case, so if we were looking at these positions of the dipole,
Is there a ground state potential?
yes, that's what I was going to try next. Look this up a little bit. So from what we found, the dipole for the ground state was actually somewhere around the value of 0.7. And so when we were looking at a type of...
Draw it. Do not hesitate.
Okay.
Draw the potential surface.
So we were looking at this value, this excitation is coming up to the second excited state instead of going directly to the first excited state. And so the initial momentum was set to 0. And if we look at that video that was playing, so the excitation occurs, and you actually see the blue wave packet shift a little bit to the right before trying to go back to the equilibrium point of the second excited potential.
So in a similar problem to what Mariah was talking about, these transfer rates are extremely sensitive to the displacement of those potentials. So how did you decide how that displacement should be between S2 and S1?
So when I ran our ab initio calculations, so I got equilibrium points at each of these. And the next step is I can take the geometry of, say, this first excited state, but then populate it with the electronic structure of the second state. And so you start getting these points that are defined by the reorganization energy. And so you can start looking at the points and how they change, and then just, in this case, we fit them quadratically. And so that was how I came to do this.
Thank you.
More questions to the speaker? If not, let's thank Jon once again. And, I would like to thank all presenters.